Okay, alright, we are on page 133. In this example, we are given the equation of two planes, pi 1 and pi 2. In these two equations, you want to notice something about these two equations, and that is, you notice that these two vectors, right? This is a vector perpendicular to the first plane, this is a vector that is perpendicular to the second plane, and you notice that these two vectors are what? Parallel to each other. So it looks like, in this case, if you have pi 1 and pi 2, they are normal vectors, right? Their normal vectors are parallel to each other. Pi 1 has a normal vector that's like this, and pi 2 has a normal vector that's like this. So when that happens, you can see that the two planes are parallel. So immediately you say that pi 1 and pi 2 are pi 1 and pi 2 are parallel since 2, 4, 6 is equals to twice of 1, 2, 3. Since the normal vector of the first is twice the normal vector of the second. So this is actually the statement. If one vector has a normal which is parallel to a second one, that means these two planes are parallel to each other. Likewise, in this example, again, you are given two planes, and by the earlier discussion, you can clearly see that these two planes are parallel to each other. When two planes are parallel to each other, what can we be interested about them? In our earlier discussion in a previous video, you realize that when two planes are parallel to each other, we will be interested to find this thing, the distance between the two planes. To find the distance between the two planes, by the earlier discussion, this distance is equals to, now, watch it. Okay. Now, to use the result that we have established in the earlier video presentation, you must first and foremost note something. This is 1, 2, 3. This is 2, 4, 6. Before you do anything, you must first and foremost change this equation into 1, 2, 3 as well. So you must always start off to make sure that the two normal vectors of the two planes, they must be identical first. It will be possible as long as these two are parallel to each other. As long as they are parallel to each other, I can always reduce one equation so that it shares the same end as the other one. So once you have done so, to find the distance between the two planes is just 26 minus the other number on the right. 26 minus this number, you see? And then divided by the magnitude of the normal vector. The normal vector that's common for these two of them. So in this case, you will get 33 divided by square root 14. This is that easy to find the distance between two parallel planes. Now, on page 134, we want to know that if you know two planes are non-parallel, these two planes are certainly non-parallel. Why are they non-parallel? Because the normal vector is 1 minus 2, 1, and the normal vector is 0, 3 minus 2. And for sure, these two normal vectors, they are not parallel to each other, and hence the two planes are non-parallel. When two planes are non-parallel, they will surely meet. And when they meet, they will always meet along a line. So two planes, when they meet, they will always meet along a line. And how do you find the equation of this line? There are actually two methods to go about it. I'm going to show you the first method now. Okay, let me show you the first method to find the intersection between two planes, method 1. Method 1 is quite straightforward. You see this as two simultaneous equations. and you try to solve these two simultaneous equations. I know you'll be wondering, say, there are only two equations but three unknowns. And the way to go about it is, we will usually let okay, there are three unknowns, right? There are three unknowns. We are going to start off by doing this one. We're going to let one of these unknown, say for example, I let z be lambda. Okay, I let z be lambda. So my equation becomes x minus 2y plus x minus 2y equals to 12 minus lambda. I call this equation 1. Say again, the first method is to solve this like simultaneous equation. I've said that you let one of the unknowns, say, be lambda. And then for the second one, same thing, you let z to be lambda, you're going to get 21 plus 2 lambda. Okay, so I have let z to be lambda, and then I have simply formed these two equations, 1 and 2 from these two equations, by just shifting terms around. And the next thing I'll do right now is to try to solve for x and y in terms of lambda as well. So from equation 2, right, from 2, my y is equals to 7 plus 2/3 lambda. Okay? Right, then I'm going to put into 1. I put into 1, my x is equals to 2y, which is 2 of y plus 12 minus lambda. So this gives me 14 plus 12 gives you 26. Then for this one is 4/3 minus 1 gives you 1/3 lambda. So once you have done this, once you have x, y, and z, so-called found in terms of lambda, we are now ready to actually write down the equation of the line. Don't blink your eyes. Are you ready? You're going to say the line is going to be x, y, z equals to, for x, right, x, the number is 26, y is 7, z is 0 plus lambda. So it's 0, the first entry, 26, 7. Okay, let me write down more clearly. This means z is equals to 0 plus lambda. So I got 0 here. Then plus lambda. For the case of x, this is 1/3. For the case of y is 2/3. For the case of z, is 1. And lo and behold, this is already the equation of the line that I want to find. And equation of line typically is expressed as r equals 2. So this then is the equation of the line that you want to find, this line. Okay, the steps quite simple, right? It is really solving a simultaneous equation. I've said that the strategy is to let one of the unknowns be lambda first. Can you see? Be lambda. I'm just rewriting it. Let z be lambda, rewrite this, solve this equation for y and x in terms of lambda also, and then tidy up. This is the equation of the intended line. Of course, you can actually reduce this and write this as what? R equals to 2670 plus, if you wish to, you can write this as 1, 2, 3. Okay. This is how you can go about finding the equation of the line of intersection between two planes. This is method 1. I'm going to show you method 2 soon. Okay, now we are going to do the same thing, but we intend to use so-called method 2. Okay, I'm going to solve the same thing using method 2. Okay, I want you to imagine that if you have two planes which are non-parallel, I've drawn it on the diagram. So maybe you can imagine that these are the two planes, right? Can you see? These are two planes. Can you see? From far, can you see here? These are two planes which are non-parallel to each other. Once more, okay, these are two planes, right? These are two planes. Sorry, I think like this, okay, like this. These are two planes, okay? Can you see the two sides of this book, right? Two planes. From far, you see like a V shape, like this, okay? Okay, then the line of intersection of these two planes, right, is like this part of this book, right? Can you see? Then if I were to do it like this, if I were to turn it this way, right? Turn this way, you want to realize that the line of intersection is actually here. It's actually here, right? So if this is the line intersection, this is the first plane, the second plane, right? For this first plane, there is actually a normal vector that's like that. Like this, okay? For the second plane, there's also a normal vector that's like this. So you want to realize that if I cross product this vector, right, with this vector, what do I get? If I were to cross product this vector with this vector, what do I get? If I cross product this vector with this vector, you realize that I'll get a vector that's like this. And this vector serves very well as my directional vector of this line, of this inverted line. Can you see? Alright. So based on this discussion, I can actually go through a step 2 by first and foremost, bearing in mind that I want to find the equation of line in this manner. The equation of line got two things, right? Got two things. So based on my demo, I hope you can see this equation, or this vector can be found simply by taking the cross product of two vectors. Tell me which two vectors. It is the vector 1, minus 2, 1, and 0, 3, minus 2. If you cross product these two vectors, you obtain a vector that will serve very well as the direction vector of this line. And this gives you, close this, 4 minus 3 is 1, close this, minus 2, that's 2, close this is 3. Can you see? So immediately I'll get this vector 1, 2, 3. Now the next thing is, now that you have actually a vector that's parallel to the intended line, right? You have found this vector. To find the equation of line, I need another thing, and that is a point on the line. A point on the line. Okay. And the way to go about it is, you just imagine that maybe a point on this line, maybe it look like this. Right? Arbitrarily, I have given a 0 to the z component. Okay? I am saying to you that I think that a point on this line could look like this, A, B, 0. Of course, it may challenge me, say it may not be possible that a line will surely contain a point that has a 0 for the z component. It's true, okay, it's true. But supposedly, I just imagine that there's such a point. If my point doesn't work, it will just try another similar point, right? So supposedly, I imagine that there's a point A, B, 0 that's on this line. And because this point is on this line, this point therefore is also on this plane. And therefore this point is also on this plane. So what can you say? You therefore say that this one will satisfy this equation, right? So therefore I will have, if I put this point inside this equation, my x is A, my y is B, my z is 0. I get what? A minus 2b equals to 12. Likewise, I put this thing in here, I get 3b equals to 21. So now what I do is, I solve for my a and b. My b will turn out to be 7, and my a will turn out to be 20. My a will turn out to be 26. Therefore, the point here would be 26, 7, 0. So therefore, the equation of the line will therefore be 26, 7, 0 plus lambda 1, 2, 3. Let me come back to the same point that I was trying to stress to you, that I have arbitrarily given 0 to the third component. There's no guarantee that it works. But if it works, like this case, it works, right? You are able to find a value of A and B. If it doesn't work, you get something that's very strange, gibberish, and you know it doesn't work. So in the event that if you try AB0, if it doesn't work, you could try 0BC, or you could try A0C. Or if you wish to, you can try AB1 also. You know what I mean? So you just try, as long as you are able to get a point. In this case, I got to a point 2670, and I can verify that this point lies on this plane, and this point also lies on this plane. I'm done. Right? I'm done. So this is somewhat like, if you like to say again, try and error method, it's true. Right? Just that you are trying out very carefully and very intelligently, you're not doing anyhow. Right? So this is actually the method 2 for you to find the intersecting line between two planes. In example 16, we are again presented to you two equations of two planes. This time round, the first equation is expressed in this form, the parametric form, and then this is actually the dot product form. And now in this question, again you're asked to find the intersecting line between the two planes. Because the first equation is given in a parametric form, we could potentially convert this into the dot product form and use the method we have earlier. Otherwise, we can actually still use the equation that it is and solve for the intended line of intersection. And how do you go about it? The way to go about it is to try to solve these two simultaneously. How do you solve these two simultaneously? Watch it, don't blink your eyes. 8 plus lambda plus 3 mu, and then I got minus 1 plus 2 lambda plus 2 mu, 2 plus 3 lambda, dot with this. What I've done is I have actually equated the first equation as collapse this as a single vector and drop it inside here, and then I get this equation. All I did was I put this inside here, and then from here I try to actually do something. What do you think I want to do here? Here I want to actually establish a relationship between lambda and mu. Okay. Say again, the method again. How does it go? Is that I drop this whole thing inside here. I want to perform a dot product, and in performing a dot product, I want to actually establish a relationship between lambda and mu. So let me plug it in. Let me do the dot product. If you perform the dot product correctly, okay, if you perform the dot product correctly, you actually get this line. Equals to 21. So I've simply just done this, no? This times this plus this times this plus this times this. That's all I did, right? So from here, right, what I'm hoping to do is in the end here, I'm hope to be able to write, say, mu. Able to write mu, say for example, in terms of lambda. Okay, this is the intention. From here, right, what I intend to do is to express mu in terms of lambda. If you're able to do so, right, then this whole thing will later on be plugged inside here. Right, replace the mu with something in terms of lambda here. And then this entire equation, it will collapse from a plane this equation will collapse from the equation of a plane to become equation of a line, because you will only be left with one parameter lambda. Okay, say again. From here, I intend to establish a relationship between mu and lambda. And once I'm able to do so, I will plug this whole thing inside here. So this be in terms of lambda, right? And this entire equation can be tidied up to become an equation of a first vector plus lambda of a second vector. You know what I mean? And that becomes the equation of a line. Okay? So if you do your arithmetic correctly, for this particular example, okay? For this particular example, if you do your arithmetic correctly, it turns out that if you do your arithmetic correctly, it turns out that mu turned out to be just 7. You perform a dot product, you find that in this particular example, it is not always the case, but for this particular example, it turns out that mu is equals to just 7. But if it insists, I can say that mu is equals to 7 plus 0 lambda. Typically there will be some lambda, but for this question, the numbers are chosen so nicely that there's no lambda, right? But in general, right, you should have something in terms of lambda. And then this whole thing is now plug it inside here. Okay? So you plug it inside here, you now have r equals to 8 minus 1, 2 plus lambda 1, 2, 3 plus, okay, let me put in s 7 plus 0 lambda, okay, to be, for completeness sake, I just put as 0 lambda, 3, 2, 1. And then this tidies up to become, okay, it was at first in terms of 2 parameters, and now with this replacement, you find that it now becomes an equation of only one parameter. This is wrong. Okay, so what we'll do is, what happens is, you're going to take 7 times this plus this. So I'm going to have 7 times this 21 plus 8 is 29. 7 times 2 14. 14 minus 1 is 13. 7 times 1 plus 2 is 9. Plus lambda of 1, 2, 3. And there you are, the equation of the intersecting line between the two planes. So let me emphasize this again, because I don't want you to think that it is always such a nice thing that you get. In general, it's not. In general, there is some lambda. But it's okay. You just have to plug it in and tidy up this to become an equation of only one parameter, and you're done. And this is the intersecting line. Right, and that completes example 16. We are now into page 136, example 17. We are interested to find the angle between two planes. If you see two planes from a far distance, it will look like two edges like this. Okay? And then if you are talking about the angle between two planes, we are actually referring to this angle. This angle theta, right? Angle between two planes, I want you to know that by default is actually the acute angle between them. So to find angle between two planes, by default it means to find the acute angle between them. This is something you must remember. Angle between two lines is also the same thing, To find angle between two lines is also the acute angle between them, and the angle between two planes is also the same. So if you are interested to find the angle between two planes, and then the first plane has a normal vector like this, I call it n1, and the second plane has a normal vector that is like this, I call it n2, then it won't take you very long to realize that if this were the case, then this angle between the two ends, is also theta. Using simple geometry, you can verify that this angle between the two normal vectors n1 and n2 is also the intended angle that you wish to find. So therefore, to find the angle between two planes, such as pi 1 and pi 2, we just need to find the angle between the two normal vectors. So like in this example 17, you are told that it passes through a point A, and then it is parallel to these two vectors, 2, 1, 1 and 1, 0, 2. Right? So if you know that these two vectors are parallel to this plane pi 1, you can first and foremost work out the normal vector of this plane pi 1 first. How do you find the normal vector of pi 1? You have already learned and by now you are quite good at it. You just have cross product these two vectors. Cover, you get 2. Cover, you get minus 3. And cover, you get minus 1. So this is the vector that is perpendicular to the plane pi 1. Then there's also the plane pi 2 given the question. The plane pi 2 has equation r dot 1, 2, 3 equals to 7. Right? And now to find the angle between the two planes, as I told you, it's just cosine theta n1 dot n2, just the way we find angle between two vectors. But there is a small exception. What is a small exception? Because we intend to find the acute angle between them, we therefore want to take this to make sure that you are finding the acute angle. When I draw my diagram like this, right, everything falls in place, so that you are made to believe that the angle between the two ends is the angle that we intend to find. However, if n2 had gone the other way around, say downwards, right, then n1, n2, okay, say again, if n2 goes downward, go downwards, then the angle sandwiched by n1, n2 is no longer theta. You will find that if that were the case, the angle between n1 and n2 will be obtuse, and it's not the intended angle you want. So for the reason, right, you want to actually put a modulus here to make sure that the diagram will be, to make sure that you're finding the acute angle. So that's very important, right? We only want to find acute angle between two planes. As I said, by default, angle between two planes must be the acute angle between them. So this gives me, what is n1? This is n1, and obviously this is n2. Dot product these two, what do you get? 2 minus 6 is minus 4. Minus 4 minus 3 is minus 7. And then because modulus becomes 7. Okay, so again, I have dot product these two. This dot with this. It is actually minus 7. It's actually minus 7, but because of modulus, I just put as positive 7. Then the magnitude of n1, which is square root 14. The magnitude of n2 is this thing. So from this, right, I can get that the angle theta is equals to 60 degrees, or is pi over 3. Right? This is how you find the angle between two planes. Just in example 17. We are now on page 136. We are interested to find the angle between two planes. If you see from a far distance, a plane looks like a line from far. So on the board, I've drawn you two planes from far. I see them as if they are two straight lines, but they're actually planes. And if you are talking about the angle between two planes, we are referring to the angle here. This is the angle between the two planes, pi 1 and pi 2. I want you to know that angle between two planes is by default the acute angle between them. Right? How do we go about finding the angle between two planes? Supposedly the first plane has a normal vector that's like this, and then the second plane has a normal vector that's like this. Right? Then, using simple geometry, you will be able to tell quite quickly that this angle that is between the two normal vectors, this angle is also theta. Why is it so? if this is 90 degrees and this 90 degrees, right? This angle will be 180 minus theta, and because these two are 90 degrees, so therefore this angle must be theta, and hence this must also be theta. So you find that to find the angle between two vectors, to find the angle between two planes is the same as finding the angle between the two normal vectors n1 and n2. So in example 17, you are given an equation, you're given a plane pi 1, and this plane pi 1 passes through a point, and then it is parallel to these two vectors, 2, 1, 1 and 1, 0, 2, right? Okay, so given this information about plane pi 1, I can at least start off by finding the normal vector of pi 1. How do you find the normal vector of pi 1? If these two vectors are parallel to this plane, I'll just cross product these two vectors to get a vector that is perpendicular to this plane. So how do I cross product? Cover the first row, I get 2. Cover the second row, I get minus 3. Cover the third row, I get minus 1. So this vector n1 is the vector that is perpendicular to the plane pi 1. And then we are given a second plane, pi 2. The second plane pi 2 is r dot 1, 2, 3 equals to 7. So by the earlier discussion, to find the angle between the two planes, it becomes cosine theta equals to n1 dot n2 over. But because we are intending to find the acute angle between the two planes, it is important for you to actually put a modulus on the numerator to assure you that you are finding the acute angle. Now, when I drew my diagram earlier on, I gave you the impression that I always have something so nice that these two vectors just sandwich the angle theta that you intend to find. Actually, if this vector n1 had pointed downwards, right? If this vector n1 had pointed downwards, right, then the angle between n1 and n2 is no longer theta, but it will be an obtuse angle. And then you end up as an obtuse theta, which is not what we want. So in order to ensure that you get an acute angle, I want you to remember that to find angle between two planes, you always need a modulus on the numerator. And now we are ready to perform the arithmetic. N1 is 2 minus 3 minus 1 dot with N2. And then the magnitude of N1, which is square root 14. And then the magnitude of N2, which is square root 14. And let's perform the calculation. This gives you 7 on the numerator. It's actually minus 7, but because of modulus, right, it becomes a positive 7. And this gives you half. So if you have cos theta equals to half, so theta is equals to 60 degrees or pi over 3. And this is example 17.